So we start with the cloud, and this is what we have in the since around 2000. That's the new buzzword. And in the cloud, we have this sort of a juicer. And the premise of the cloud is that you take an orange and a tomato, you put into the juicer, and you get orange juice and tomato juice. And for some reason, when I show that, everyone smiles. But when we look at computers, we don't think this way. We believe that we actually get orange juice and tomato juice. And there is a very good reason for that. Because when we start studying computer science, we're told that the computer is a central processing unit that takes an instruction from memory, executes it, writes data back to memory or to the output, and then goes to the next instruction. And sometime when we go to second year, we see a diagram like that, or even more complex in the computer architecture course. And then we continue with the rest of our computer science degree. And in our computer science degree, we learn about high-level languages. And we are interested in asymptotic rather than concrete performance. And the architecture is a minor topic that appears in second year, and that's it. And we focus on abstraction. Abstraction is the magic word of computer science. We can't do anything without abstractions, and we have to rely on them. And then we have CPU vendors' interest that don't really want us to know what happens inside their computers, partly for good reasons that allow them to upgrade their computer without us having to rewrite all our programs. Partly is for less good reasons. It allows them to keep an edge over the competitors. So we end up with, even though we have seen, everyone has seen what computers really do and what they look like, or to some extent, we still think of computers as von Neumann architecture. And that creates this divide between software and hardware. In the software, we work with the instruction set architecture, or the, what we see, what we program to. And then there is this microarchitecture somewhere underneath. And inside, we have all sort of components. And while we don't see these components when we program and we don't think about them, they do affect the way that we work. And that creates a gap between our abstract view of the computer and the concrete instantiation of the way that the computer works. And that affects in several areas. I list 3 of those here. First thing is we always think about hardware as dedicated to us. All our programs assume that no one else runs on the computer. So we know that that our programs are not the only thing that runs there, but it almost never affects us. In real life, computers are shared at multiple levels between threads in our program, between programs that run in our operating system, or between multiple virtual machines that share the actual hardware. Second thing, we think about memory access as uniform. Memory access in a program takes O1, that's constant time, and that's it. In practice, we have a hierarchy of caching and hierarchy of predictions that makes access non-uniform. And it happens at all levels. Again, it can be the caching inside the processor, or what is in registers, what is not in registers. It can be between the processor and the main memory, and it can be part of the operating system pages out pages, and we need to access them or wait for the operating system to bring them into memory before we can access them. And the last thing is that we think of execution as serial. We take an instruction, execute it, write its results. Takes the next instruction, execute it, write the result. In practice, the processor is superscalar, so it has multiple execution units that all of them execute in parallel. And again, it occurs in several levels. The more familiar ones are the fact that we have multiple CPUs, multiple cores, but even below that, we have multiple ports in each core that can execute instructions in parallel, and the instructions execute in some arbitrary order, not necessarily in the order that we wrote. So we have an abstraction, we have the concrete instantiation, and there is a gap between them. And when we have a gap between abstractions, we have security problems. And what I'm going to do today is describe some of the things that I and others have worked on in exploring this gap between the abstract or nominal view of programming, of program execution, and the way that the processor actually works. And I will start with basically with cache attacks. So the impact of memory uniform and non-uniform versus non-uniform access. And in the second half, I'll go a bit about on transient execution attacks, where we look at the execution order. Any of you who have worked with these, will be probably a repetition. It is an introduction. The aim here is not to expose the bleeding edge of research into this area. The aim is to give you some, to give those who are now starting to look at this area or may be interested, some information on how or what we do here, how things work. So let's start with the first thing on CPU versus memory. So here we have a photo of my first computer. That's an Apple IIe. It tells you roughly my age. I was able to work with computers when they came out. It has a very fast processor, 1 megahertz. And when you think of that, 1 megahertz, that allows that computer to do 1 million additions per second. That's really quick execution. So it's much faster than we can work. And here we have one of the, what's already not so recent machines that I bought, probably 3 years old. It's a Intel NUC. It has 4 cores, 8 hyperthread. Each of them runs at 2600 megahertz, so 2.6 gigahertz. So in the years between 1980, I don't know how much it was when the Apple IIe came out, and 2017, we gained about 4 orders of magnitude in speed, in processor speed. At the same time, memory also became faster. So in my Apple IIe, memory has a latency of 500 nanosecond, which allows the processor to access memory twice per cycle. So each instruction that the processor executes, it can access the memory twice, which is relatively good because we need half a cycle to bring the instruction and half a cycle to bring data, and we can do things in 1 cycle. The NUC has a memory latency which is faster, so it's 63 nanosecond, and that's 1 order of magnitude. There are also areas that it gains some more speed over the Apple, but overall we gained around 1 order of magnitude. And that created a gap between the speed of the processor and the memory, and the speed of the memory. And what happens is if we have our memory and we have our processor and we need some data, then it takes some time for this data to get to the processor. And if we need this data again, as often happens in programs, or if we need related data soon, then again, we have to wait a long time. And if we leave things like that, what will happen is that we have a processor that can do 10,000 instructions per 10 billion instructions per second, but it needs to always wait for memory, for data coming from memory. So to bridge this gap, processor engineers, what they do is introduce a small bank of memory that we call a cache. And this bank is because it is smaller, and because it uses a much more expensive technology, and because it is closer to the CPU, it is much faster. And the cache exploits the locality of programs, so the fact that programs access most of the time, they access data that is in the same location or very close location to location they accessed earlier. And it exploits that to speed up access to memory. And the way that we do that is that when we read data from memory, it goes through the cache, and the cache stores a copy of that data. The next time that we need this data, we'll get it from the cache. and that will be faster. And the cache runs at an order of 4 cycles, 1 access per 4 cycles, so it's about 2 orders of magnitude, and we bridged most of the gap between the processor and the memory. Now, when we use cache, we can have a problem that the data in the cache may get out of sync from with the data in the process, in the memory. For example, when the memory changes without going through the cache. Now, this is extremely rare these days. It was much more common in the 90s, but it probably is still possible, and we need some way of handling that. And the way that we have, that Intel gave us to handle that is this will create us a problem that we read stale data. And the way that we have to solve this is we flush the cache. So we have a special instruction in Intel processors that what it does, it tells the cache, remove this data if you have it. And that ensures that the next load will come from memory. It will be much slower, but at least we'll get fresh data. So now what we have is we have two memory speeds in this example. One, when we get data from the cache, it is fast, and when we get data from memory, it is slow. And now we want to exploit that, and exploit that we'll use the first attack that we have is Flush+Reload. It's was published in 2014, and what we have here is a spy, and we have a victim, and the spy and victim share the cache because they run on the same processor. And the way that the attack works is that the spy flashes, sorry, my animations are broken. The spy flashes a memory line from the cache. It then waits some time, and after it finishes waiting, it reads the line again. Now, because the spy flashed it from the cache, it will not be in the cache, and it will take a long time for the spy to get that data. However, if the spy flashes the memory from the cache, and while the spy waits, the victim accesses the same memory location, then it will be cached again. And when the spy accesses it, the access will be fast. So the spy can distinguish between access and no access to the cache, to this memory line, and we can build and learn something that the victim has done. Now, if you want to try to do that, you can read the paper and find the code in the paper and try and play with it, and you will find out that yes, it works, but you'll have to tinker a lot to get it working well and to get good results. So to save up some time or some work for people, we developed a toolkit that we call Mastic. It's basically it's an acronym for a microarchitectural side channel toolkit. And originally we aimed at get some information and reduce barriers to entry into the area. We have some implementations of side channel attacks. A new version is coming up soon. And if you want it, you can download from my homepage. I'll give the link later if anyone is interested. And let's look what a mastic attack looks like. We have here an example of a code that currently exists in mastic demo. So we have a program, and what this program does is monitors access to its own source code. And the way we do it is we allocate an abstraction for a Flush+Reload attack. We then tell it what to monitor. The way that we do it is we have a way of giving it a file and offsetting the file, and it will continue, it will monitor this location. And we run the attack, we probe what happens in this location, and if the time is larger than 100 cycles or smaller than 100 cycles, we know that the file has been accessed. So now I'll try to demonstrate this in real life. For this, I'll need to move to a different computer, and I apologize in advance in case I get any problems. This is the first time that I'm trying a live demo on Zoom. So let's see if we can get it to work. So, okay, so here we have our program. That's the same program as earlier. And I'm running it. In a different window, I do cut of its source code. And we see some accesses. And I can repeat that. Let me go to that now, so we don't see too much noise. And every time that we try, we see it. We see the access. Okay. So that's one thing that we can do. We can monitor access to a file. More interesting, if we look at if we make slight difference, slight change to the function, and we have, instead of monitoring something that came out from a file, we monitor an address in the C library, then we can see whenever a program executes this function. So let's run this. And now I have a function. I have this a small program that all it does is output hello world. And whenever I run it, we see a call to put this. So we can actually monitor accesses to functions in different programs, which is not something that we are supposed to be able to do. I don't show it here, but it happens. It also works if we have multiple users. So it works with multiple users, and the attack works that way. Okay. If there are any questions, please send them. I'll try to see, or someone make it. So let's go back to the slides. Okay, now how does this become an attack? How does this become an attack? For an example, we'll use an attack on RSA encryption. RSA, just a quick reminder, is a public key cryptographic scheme. We have Alice and Bob. Alice does some strange maths to get public and private key and sends her a public key to Bob. Bob wants to encrypt the message M, and what he does is raise M to the power of E modulo N, send that to Alice. Alice does raise C to the power of D, which is her private key, and gets M. This is the way maths works. I have a question, whether the cache attack will work on different users. Yes, the attack works between different users. It works between virtual machines if we have sharing of memory, and it works across all security boundaries, and can work against root users. So now what we will try to do, we want to find Alice's private key when she executes, when she does this calculation. So to be able to do that, we need to understand how we calculate C to the power of D modulo N. And remember that that all numbers here are very big. So we're talking numbers that are 2,000 to 4,000 bits each, typically. And the code that we use, the algorithm that was used in GNU PG 1413, it was changed after we published this attack. And it's called a square and multiply algorithm. The algorithm basically scans the bits. Let's see if I can do that. Yeah. The algorithm scans the bits of the exponent from the most significant, can we see, from the most significant to the least significant. For each bit, it squares its accumulator. And if the bit is set, it also multiplies by the basis. Okay? So it's a very simple algorithm. And so let's take an example. The example is, let's raise 11 to the power 5 modulo 100 and see if we get the right result. So 11 to the power of 5, if you punch to a calculator, it's 161,051. Modulo 100, that's 51. We hope to get that. Don't use these numbers if you need to try real encryption. They are not secure. So the way that we'll monitor, we'll test that is what we learn or what we teach in first year and then no one does. We'll track the variables as we go. And what we start is x equals 1. That's where we set it in the first line. I equals 2 because that's the size of the exponent minus 1. And the exponent, we have 101. And in boldface, we see the bit that we are handling it now. And the first thing that we do is square x, and 1 squared is 1, and reduce that modulo 100, and that's 1. And because the bit is set, we multiply by 11, we get 11, reduce modulo 100, we still get 11, and we are done with the first bit. For the second bit, we square 11, we get 121, modulo 100, it's 21. And because the bit is 0, we are done with this bit. We don't go to do multiplication by the basis. And then we do square 21 square is 441. Reduce modulo 100, it's 41. 41 times 11, the bit is set. We need to multiply by the base, and we get 451. And reduce, we get 51, and that proves that our algorithm is correct. Right? Well, not really, but this is not the important thing. The more important thing is that if we look at our sequence of operations here, then we have the private key encoded in this. Sorry, I'll also join my own Discord. We can see the private key encoded in the sequence of operations. If we have a sequence of square, reduce, and multiply and reduce, we know that the bit was 1. If we see a sequence of square and reduce that is not followed by a multiply, then we know that the bit was 0. So now we need to do an attack on something like that, and we'll try to use mastic again. So just first, we'll look at the code for the attack. And here we have the example of code for the attack. We tell mastic that we want to monitor 3 locations, the multiply, modular reduction, and square routines that it has. And we just specify the C lines for that. Then we have code that, as before, prepares our attack. We tell it what we want to monitor, and as you see, we have all the functions we created just for you, all the functions that translate a program location in a C code location to a binary, to the code location it exists in the binary, and we tell the Flush+Reload that we want to monitor that, and we arrange some space for our results. So we want to collect the results in memory because if we print them, it will take too long. Second half of the program, we actually run the attack. That's a single instruction, and we output the results. If you don't want to program for Flush+Reload, we have an even simpler approach. We have a program that just gets everything in the command line arguments and does the attack. And let's see what we get if we try to run this thing. And so we have this attack code, and we run that, output the data. While it runs in the background, we execute one decryption operation and plot the results. And of course, it didn't work now. Let's try again. Why didn't it work? I have no idea. Beautiful. So now what we have here in this trace, can you see the cursor? Yes. On the x-axis, we have we have time, and we measure time in samples. The program measures the cache every 2,000 cycles, as far as I recall. Yes, cycles. In the y-axis, we have the latency of access to the memory location, and the graph shows the latency of accesses to memory locations of the square and the multiply routines. And recall that when the access time is high, that means that we bring data from memory, so the victim has not accessed the location. When the access time is low, that means that the victim has accessed this location, and therefore the data is in the cache. And then when we look at that, here we see that we have an access to multiply just at the beginning. Sorry, we have the access to multiply, and immediately we see access to square and access to multiply. And that tells us that the victim was processing the bit 1 there. And then we have access to square, and then another square without a multiply in between. And that tells us that the victim has accessed the bit was processing the bit 0. And then we have another square and multiply, and we have another 1 bit and another 1 and a 0 and 1. I hope that you can trace with me, yes. And another 0, another 1, and we can continue reading this data until we get to the end of the exponent. So we basically broke the private key. Just an interesting point, just because we get it here, as you can see at this location, we have access both to the square and the multiply. And the reason that this happens is that the processor tries to guess whether the victim will, or the processor tries to predict where the code will go, and it predicts here that it will go directly to the next square and skip the multiply, and it just makes a mistake, and therefore we do see access to the multiply, even though there is no, do see access to square, even though the program does not really do that. Questions? Yes. We are monitoring the functions that perform the operations multiply and square. Yes, just like we did with putTest. Although in putTest we use the library that we are actually using. We'll use libc. Here we need to map the code of the victim because the code does exist in the library. Okay. Cool. So let's go back to slides. Okay, we did the demo. So basically what we have an attack that can leak information on victim access to shared memory. And we can monitor, because code is typically shared in the victim access to the code, and from the access to the code, we can infer what the data that the victim operates on. But what if we don't have access to the same code? So, for example, if these are two virtual machines that do not share memory, or if we try to monitor access to data that the victim has changed and we don't have shared access to it. So for that, we need to go to another attack, and we'll look at the Prime+Probe attack. That's a slightly older technique from 2005, Osvik, Shamir, and Tromer. And it's based on the way that the cache is constructed. So modern caches are what we call set associative. So they have a sequence of sets here. And each set can store some, so each memory location maps to a set, and each set can store some data or some memory lines. And the way that it works is that we have memory mapped to the cache set. So every cache size instructions or cache size memory location will get mapping to the same location. And when the program accesses some memory, it comes from memory to the cache and stay there. And if it accesses another location that maps to the same cache set, it goes to a different way. And now we can access these memory locations quickly. If the program now needs another location that maps to the same cache set, it will take time to bring that, and it will evict some of the old data from the cache, and the program and will replace it with the new data. So now accessing the purple location will take longer, but the orange and green are fast. Use that for an attack. And again, we have our spy and the victim and our cache. And what the spy does is allocate a cache-sized memory buffer and then access all these locations. And we call that prime operation because it prepares the cache for the attack. And after this access, the cache will be full with the victim, with the attacker's memory, with the attacker's data. The attacker now lets the victim execute. And when the victim executes, the victim will access some memory locations. After the attacker finishes waiting, the attacker tries to read data from the buffer, and it does it by set by set. So it first accesses locations in the first set. And because this set has not, the victim has not accessed memory that maps to this set, then everything will be cached and the access will be fast. If, on the other hand, it accesses a location that the victim has accessed, then access will be slow and memory, and so the attacker can know which cache sets the victim has accessed. And again, we repeat that, and we will look and we get the attack, and we just repeat this, and we find which cache sets the victim has accessed in each memory, in each round, each attack round. So let's do an example again, and we'll do a simple victim, what we call a rattle. It's just a program that creates an access pattern that we know, and we can search for it in the cache and see if we get what we expect. So what this victim does is very simple. It has a buffer of 4096 bytes, and it does an infinite loop that for 64,000 iterations, it accesses one location at offset 800, and another 64,000, it accesses offset 1800, and keeps repeating that. And let's see what happens when we monitor the cache when we do that. So we run our rattle. We need to tell it on which core we do that. And then we run in another core, we run a program that just monitor the L1 cache and plot the results. I don't see it on my other screen, so I assume that, oh, there it is. Plot the results, and we get this nice diagram. And there is quite a lot of data here. So again, on the horizontal axis, we see that our time is the experiments that we have done. In the vertical axis, we have the cache set. The Intel L1 cache has 64 cache sets. And the color indicates how long it took to access that cache set in that iteration. So it counted in cycle between 50 and 90 cycles. And when we look at that, we see a patterns around cache set 30 and cache set 12 of alternating accesses between the two, which is what we expect from our victim. Now, there are other interesting patterns here that I'll briefly describe just because it shows how much we can learn from these cache accesses. So we have these two horizontal lines And these horizontal lines are the stack locations of the spy and the victim. They both run on the same cache, and both of them has a stack that they access during runtime. So one of those is the spy and one of those is the victim. I don't know which is which, and it changes every time we run that, so I can't even tell you. The other thing is that these diagonal lines, it turns out that these lines are our spy when it writes data, the data that it collects from the victim. We see the location in memory that it writes. It just goes in a linear buffer and writes data, writes, advancing over the cache, and then wrapping around to the start of the cache again. Okay, so we can see things that happen in memory. Let's go back to the other screen. So for an attack, we'll look at AES for a real victim. And the code of AES with T tables, and this is the code, and no need to worry, we're not going to explain everything here. What we have here is basically 4 lines that get our input data and do exclusive OR with the key. To the question, the spy and victim are running. Okay, the example that I did, the spy and the victim were running on 2 sibling core, on 2 on the same core. There were 2 hyperthreads of the same core, and the attack was on the L1 cache. In Mastic, we have an attack on L3, which can also get data across cores. So back to AES, and then what AES basically does is getting a lot of data from some tables based on its current state, and just keep changing the state. And these tables look like that. Also, for all purpose, we can think of that as random numbers. And the important thing that we look at is we just look at the first byte, or at the first word of data. What we do here, we get the input that the user asked to encrypt. We do exclusive OR with 1 word of the key, and then we use the top byte of that as an index into one of the tables. So let's focus on this code. And now, if we assume that we can somehow find what the index is, and we know the plaintext, what this gives us is that the operation, that exclusive OR that we do to calculate the index from the plaintext and the key is reversible, and we can recover the most significant byte of the key with that. So what we will try doing is, during the same attack, we'll just run the encryption, do prime before the encryption, probe after the encryption, and see which cache sets are accessed and for which plaintext byte. So the idea is just repeatedly doing it multiple times. The reason that we need multiple times is first because we have some noise in the attack itself. So access times do vary, and we need to average over multiple accesses to get the real access time. And the other reason is that because we don't know what happens with the victim has multiple accesses to the same to each table. I think that yes, it's 40 accesses to each table. In some cases, just by chance, a plaintext will give us an access to a cache set, and to the cache set that we try to see which byte maps to. So we need to run multiple plaintext and average things over time until we get the results. Now, I will not show the code, partly because it is slightly more involved, and partly because it is not yet released. So it is the next version of Mastic that we expect to release in hopefully this year. But I will just show the result of running that. So let's wait for the screen share to work. Yes, it is updated. So what we have, I'll show a little bit of the code. What we have here. What we have here is a simple program. We have a crypto function that what it does is basically takes three inputs, an input buffer, an output buffer, and some data, which is the key, and uses it to call AES encrypt. And then we have a function, the main function, parse arguments, which we'll ignore, and go and does the attack. And the whole attack is just in a single function call. That's the main attack. All the rest is data analyzing the data and presenting it. And what it does, it just takes runs the encryption many times and split it based on the plain text byte to see what the key to try to see if we get the key from that. And if we run it, after some time, we get the results. And the output, this outputs all the result, all the key bytes, and that also does the analysis to find out the data that shows us where the byte is, or try to guess the byte. And again, we have in the horizontal axis the cache set. In the vertical axis, we have the first 4 bits of each key bit, and we highlight here the guess. We can run it with a little bit more samples, then it will be much clearer to the when we look at that. It just takes longer. It does work nicely. I know why. Sorry, we have too much noise in the cache at the moment. This one is still running. Hopefully it will look better now. No, I don't know. Doesn't get best results. Let it run a bit more. Got to love the live demos. Okay. So far, question. So far, we are focused on Intel architecture. How does it affect ARM? So ARMs are vulnerable to Prime+Probe. Some of them, under some circumstances, vulnerable to Flush+Reload. They have other vulnerabilities, so they have other microarchitectural components, and many attacks do work on ARM, but not all. Intel tends to be usually much easier to attack. This will also happen on transient execution attacks. Intel is particularly vulnerable. Okay, I'm not going to wait here. We'll probably come back later to that screen. On AMD, oh, here are the results, sorry. So when we run it longer, you see that this is much higher, much easier to see. The red hashes are things that the program adds, but the color highlight, the color scheme tells us where we have faster access depending on cache set. So for AMD, Prime+Probe attacks work. Flush+Reload do not. They do not work across cores. So you cannot do a Flush+Reload between cores on AMDs, at least through to AMDs up to 2018. I haven't tried on the newer Zen architecture with the hyperthreading. So I don't know. Okay. Going back. So we had the demo. That's actually the end of this part. So with that, I guess I'll try to connect to Discord and we'll be happy to take some question on that. And before we move to the next part, I suggest that we will take a break. So first people have some time to rest a bit and for me to be able to get some water. Sample code. For sample code, I guess that most everything that we have seen can be in this location. So you can download Mastic from there and then compile and run it. Read the file, the little documentation that is there. Well, before you compile and run, you need to install some packages that it's not really highlighted well enough there. And hopefully we'll have a new version of the code soon, which is much better. Other questions? Okay, so about hypervisors. Until 2014, VMware shared memory between virtual machines and Flush+Reload worked between them. Prime+Probe still works between virtual machines, assuming that they share the cache. And other attacks that doing the same type of attack on different caches. So we have the translation look-aside buffer that we can attack. We have the branch prediction mechanism. All of those continue to work, and they work well between virtual machines, assuming they run on the same on the same core. Attacks cross cores are those that work on last level cache work, and those that work on memory do work, but you need a resource that is shared between hyperthreads, between cores for the attack. Okay, so I guess that with that, I will hand over to the organizer to say when and or to decide how we come back and when. Or I'll do that. What time is now? Now is 3:30, I think, in India. That's the time that time zone that we are doing. So let's come back in. Oh. 30 minutes. So, okay, so let's meet again at 4. Yes, it will be 4 p.m. India. That's half an hour from now.
Yeah, thank you.
Thank you.
So I guess we are back after the break. Still waiting for you.
I am back.
Okay, good.
We are back to.
So then you can continue.
Yep. Let me try to share the screen again.
So Yuval's tutorial is going great. I'm getting feedback like excellent video so far. Excellent tutorial. So best of luck.
Thank you.
Next part.
Thank you. Happy to hear that. Okay. So now let's look at a transit. It's something relatively new. Until now, what we saw is that programs, when they execute, they leak data on what they are doing. And in particular for cryptographic algorithms, there are techniques that prevent the leakage. There are techniques that ensure that all memory accesses and all execution paths do not depend on secret data. So they don't leak any information. Other techniques are hardware acceleration inside the processor. So AES and I, for example, these instructions simply don't use the cache, so they don't leak through the cache. And until 2017, Intel's response to any such attack was, hey, program your cryptography more secure. And this is not our problem. And then we published, or we reported to Intel, and then later published the Spectre and Meltdown attack, and this changed the. I think it created a lot of interest in this type of attacks because suddenly we could attack almost everything that runs on the processor. So let's start understanding this. It is a bit involved technically, so I hope that everyone will be able to follow. Let me know if I'm running too fast. So let's look at an example of a program. So we have a small program in assembly, and no need to, this is not real assembly, so it makes it easier. And what we do here is we take a location, memory location that we call base, loaded into register R1, like take location called height, load it to R2, and then do basically calculate the length of the hypotenuse of the triangle and its area. and the and the area of the triangle. Now, when we think of execution, the way that we think is first execute load base, and we get a number into register R1, and then we execute load height, and we get a number into R2, and we multiply R1 by itself to get R1 squared, and so forth. Now, so far the program continues. However, when we look at these programs, we can observe that there are some things that we can do faster. So there are while we execute the first load, we can also execute load height. Nothing prevents us from doing that. So what we try to do is do it faster. And the way that we do it is we just try to look at dependencies between instructions. We basically look at our program as a data flow graph. And we say that, well, we can do load base to R1 because it does not depend on any previous instruction. The same for load height. And then mul R1 by R1, R3, this one, we can do once we get the value of R1. It doesn't really matter where in the program this instruction is. As soon as we get R1, we can do this calculation and get R3. And as soon as we calculated these two instructions, then we can go to the dependent instruction. So basically, the processor can reorder things and do things faster. So in practice, as an example, we can start with the two loads. And when they complete, we can select which one of the three next instructions to continue and so forth. And that creates, and then we get what we call out of order execution, which basically works this way. We start executing the first load. And then while it runs, we start executing the second load. And now we will need to start making assumption on what happens first. So for example, if height is cached and the base is not, then this instruction might terminate before the first instruction terminates. And then we'll be able to start executing the multiply instruction and continue with some parts of the execution but we still have an instruction that hasn't completed execution and the following instructions that have completed execution. And we don't see anything in the register, in the architectural state. So when we look at that, there's no data there. These calculations are kept hidden in the microarchitecture. And only when the first load terminates, we can retire the two completed instruction and commit the results. And suddenly we'll have the values in the register, really have the values in the architectural state in the registers, and the program can continue working. And then the program can proceed and do whatever it wants. So basically, we got a different order of the program. We just do some topological sorting that the processor decides is faster, and we get significant performance improvement with that. So this is a technique that came in the to mainstream processors in the late 80s, early 90s, and been working there since. So, but there are issues that can happen and can affect us. So for example, we start executing the second load after we started the first one. And it turns out that the address of height is invalid. And now what happens is that the processor cannot stop at this stage because we cannot raise the trap at this stage because the first load, this load has not completed. So we can't raise a trap at this stage. So what we do is we mark this as an error, and meanwhile things continue to execute, and only when all the earlier instructions retire, we raise the trap. So while our program, while we have an instruction that is going to fail, things can continue executing, either things that, definitely everything that exist earlier in program order continues executing, and things that after that in program order can continue to execute because they are in a different topological sort. We just started executing them earlier and we continue to execute them. And it turns out that on Intel processors, when this load fails, instructions that depend on it may also continue executing. And that brings us to a new continue to the first attack, and that would be the meltdown attack that exploits. Now, before we go to real meltdown, let's look at a simple example of a weird way that we can read data. And what we have here is we have our memory. So in memory, we have an array, and we have some pointer that points to some data, which has the value 3. And we have a program that reads 3 from memory and just access array based on this pointer. And then we have our cache, and we will assume that this location is cached. And we will assume that our pointer is cached, but that the array is not in the cache. Nothing, no part of the array of the cache. And let's see what happens when this program runs. So the first thing is we dereference the pointer, and we get the value 3. And then we access the array, and that brings the location, specific location from the array into the cache. Okay, I have a question. The question is that many of these attacks are based on optimizations that hardware makes to improve average code faster, and whether there is work to introduce crypto flag or something that will make instructions to guarantee deterministic execution. The answer is yes, there are some efforts on that. I don't recall any one specific link that I can provide now. And there are some things that we know are being executed or being developed, but are not public at the moment. So now, going back to our meltdown, to our program, we have this we read this thing, and now we want to, from an outside agent, to find out which value was read. And for that, we'll bring our friend count, and everyone, I hope, remembers them from childhood. And the way count works is guess the number. So the first thing, you'll guess whether it is 1, and access array of 1 times 256, and that will take a long time. Because it takes a long time, count knows that the value wasn't 1. And then you will repeat that with 2, and again, it will take a long time. And we'll know it is not 2. And then we'll try 3, and this will come fast. So count knows that it is 3, and now we have all the Sesame Street starting to dance, and the number 3 falls for a round, and we have balloons, and everyone is happy, and we found number 3. Now, this is a bit of a weird way of finding the number, because we already know what the number is. But now we'll remember this way, and we'll change the scenario a bit. And in our new scenario, the pointer, instead of pointing to location in memory, it points instead of having the pointer pointing to location in user space, it points to a location in the kernel space. And the kernel space is part of the address space of the program that the processor guarantees is protected. So any access to this will cause the program to fail. It will raise an exception, and the program will crash. And recall that what we said here will happen is that we mark this instruction failed. This is the equivalent of the load height here. But while we are waiting, dependency instructions start executing. And that includes the instruction that we load. So if we look at our the way that things work in the process, so we have our execution engine, and it gets a virtual address, and it needs to read it, to read the data. So what it does, it converts to a physical address, and then sends to the memory pipeline. It sends the physical address to the L1 cache, and if the data is in the L1 cache, the data goes back to the execution engine. What happens when we have a trap? We get the virtual address, we try to convert it to a physical address, but the physical address is not accessible. So we have a trap here, and the processor knows that it has to stop executing this instruction, but it still happens to send it to the L1 cache. And if we have the data in the L1 cache, the data goes back to the processor. So what we have here, we are dereference the pointer, and for a while, we get this dereference working. We access array, and we get the data coming from the array to the cache. At some stage, the processor will realize that this instruction is illegal and will block it, and will say, let's drop everything that happened after this instruction. So we will not commit any results. So it realizes that and drops everything that happened. What we can now do is bring again count and check whether this is 1, and it is not 1. Check if it is 2, and it is not 2. Check for 3, and we found the number 3. And that's really dangerous, because what we got here is the ability to read a byte from the kernel space. The kernel space is supposed to be inaccessible. What makes this even worse is that not only we can read the data in the kernel address space also has part of the memory, the physical memory mapped into it. So basically, by using this technique, we can read all data that is in the processor, in the computer's memory. And that's it's a major security vulnerability, and we need to fix it. So to fix it, we'll look a bit at how this attack works, or why the attack works. Basically, we have 4 conditions that we need. We have that error instructions are not handled immediately. Instead, the processor waits for them to retire. Until they retire, dependent execution may continue to execute with some unsanctioned data, so with some data that they were not supposed to access. And then we leak this data through microarchitectural state. So Intel needed to fix this thing, and it is extremely hard to fix things that are inside the processor, because the processor is hardware. We cannot send a new transistor as a software patch. So this fix focuses on the fact that we have unsanctioned data, and what we want to do is prevent the processor from accessing this data. And the countermeasure called KPTI, or it's based on earlier work called Kaiser, it's basically we use a separate address space for the kernel. Instead of using the same address space as we've done since the 60s or 70s, we now have 2 address spaces for each process, one for the user space and one for when running as kernel. And we have some code that just flips these address spaces whenever the program executes in a system call. The main problem with that is that it introduces a huge overhead. So more modern processors include some fixes in hardware, and basically what they do is that instead of reading the data, they read 0. Okay, so Intel fixed that, and when the attack was published in early 2018, the patch was also public, and everyone could take the code, and we started working on something else, and then came Foreshadow. And Foreshadow is based on the fact that this is not the only problem that we have. The crossing the user kernel boundary is not the only fault that can happen, and other things can go wrong. And there are three variants of Foreshadow. When Foreshadow OS works that by exploiting pages that are marked as non-present. This happens, for example, if our operating system decides to page out one of our pages, so write it to disk to get some more core space, some more RAM space. And so it takes parts of our process, send them to disk, and it maps our page is not present. But when it does that, it still keeps the physical address as it was earlier. And that means that now we can read whatever data the operating system put in that physical address. Foreshadow VMM is even worse because it turns out that if the translation fails in the middle, then the address that caused the fail is used as if it were a physical address. And that means that processes running in virtual machines, virtual machines can read any cached data from any location in memory. And finally, Foreshadow SGX can leak any data in L1 from SGX, and we developed the techniques to also move data from SGX into L1, so we could read everything in SGX, and that's SGX, the software guard extension, supposed to be unreadable to anything that runs on the machine. After fixing these problems, we found out that there is even more things happen. So what happens if the data is not in the cache? Basically, the physical address goes to the L1 cache, and now, if the data is there, we have Meltdown and Foreshadow that exploit this. If the data is not there, then what the processor does, it tries to bring it from memory, and the way to bring it from memory is we have what's called line fill buffers, and these keep track of requests from memory. And when the data is accessible, what happens, the physical address goes to the line fill buffers, and they start bringing data from somewhere below. When the data arrives, they can send it both to the execution engine and to the cache. The microarchitectural data sampling attacks show that all these buffers that the microarchitecture uses for controlling data or managing the access to memory can leak. So we have the MDS attacks from the line fill buffer, from the store buffers, and from load ports and some other locations. And as a bonus, we also found other ways of making instructions access data that unsanctioned data. So microcode assists happen when instructions get into a situation that is not simple, rare situations that they need to solve with some more complex code. The way they happen and that it works is that the instruction is stopped and restarted with a microcode program. So it replaced with a small program, and for all perspectives between it, this behaves just like a trap. And TSX aborts. TSX is the Intel transactional I don't know what S stands for. Transactional extension that allows executing multiple instructions as if they were a single transaction. So either all of them succeed without affecting any other's code, or none of them succeeds. And it turns out that when transactions abort, again, weird things can happen in the processor. So Intel used the same type of countermeasures and blocked these attacks. So these are all the meltdown types attacks, all the attacks that, or some of the attacks that work by when an instruction fails. And then there is Spectre, which is similar but different. The way that Spectre works is, as we said, instructions start executing before the execution really reaches them. So we have the control flow graph, the data flow graph, and we execute instructions when the data is ready. But programs have some control flow, and they have some instructions that could continue in multiple directions. So if statements translate to conditional branches, or virtual method calls translate to just branches to addresses based on data. And we need to handle those. And because branches are relatively frequent, if we need to wait for the branch from the branch condition to be evaluated before we continue, that will take a long time. So instead, what the processor tries to do is we have execution reached to the branch. So we had the processor committed all the instructions in this part, and it has some instructions that are speculatively executing. So it guesses what will happen. It knows what will happen, tries to execute them. And now it needs to decide what will happen in the branch. And the way it does that is it has a predictor, it has a fortune teller that tells it this branch will go, it will be a true, or the condition will be true or false, and the fortune teller, and the processor follows the fortune teller. So in this case, we have the fortune teller telling it that it will go to the left branch, so the execution proceeds in that direction. At some stage, the processor will compute the condition, and then it knows where the branch is supposed to go. And if the prediction was right, we gained a lot of time, or we gained a lot, and our performance is much better. We can continue executing. If the prediction was wrong, what we do is we just drop everything that was calculated there and move to the other branch, and we lose performance because we mispredicted, but we are not worse than if we were waiting for the data to come. So this is a very good optimization, and it helps a lot with improving performance. And technically, we have two main branch predictors. There are a few others that have also been exploited, but I'll talk only about these two. The branch history buffer predicts the outcome of a conditional branch. So whether a program will take a branch or will and the branch target buffer predicts the of indirect branches. It just tells us where the program will usually go. So if we take a virtual method of a function of a class, it will tend to point to the method that we usually call, to the actual instantiation. So how does the Spectre attack works? We have again the example of an if statement that tests for size of an array. And then if we access this, if the index is within the array, we access that array. And what our attacker does is cause the victim to execute with a small value of x several times. And when it does that, it compares x and the length and access array and move it to the array 2. And while this happens, our branch predictor looks at the branch and predicts that the branch will, in this case, not be taken. So we don't jump around the code, and remembers that. When the branch predictor learned that, the attacker calls again, now with a large value of x. And we again look at the cache, what happens in the cache. So with large x, we need to start executing the to decide where to go, whether it's if goes, and we don't know what to do. So we do this comparison. This will take some time because we don't have array length. It will take it time to get to the cache. While we are waiting for this to come to the cache, our branch predictor tells us that the branch is not taken. So we continue to execute. We do a reference, and because x is large, it goes well beyond the bounds of the array and get some secret data. We then reference the second array and bringing the data into the cache. And again, at some stage, the array length will get into the cache, and then we know that we have mispredicted. We throw away all the calculation that we have done, but at this stage, we do have a footprint of what happened in the of what data was read. So we can recover the secret data. Again, we bring count, and it tells us what the data was. Now, this attack is particularly dangerous when we have environments that have secure languages. So, for example, in JavaScript, this array test here is implicit in the programming language. And that means that we can now write JavaScript code that will allow us to read everything in memory. And again, we demonstrated this attack that we can read data that we are not supposed to read. And a lot of browsers changed their behavior to protect against that. And so it's much more difficult to do this attack. Particular Chrome, the main defense is that they do not run, or they run multiple processes, one process for each domain. So we cannot use this attack to read across domain boundary. Second variant of Spectre is similar. We have an attacker and the victim running on the same processor, on the same core, sharing the branch predictor. And we have an attacker and the victim code, and the victim has some indirect branch that goes and the victim also has a location that behaves like the read from memory and then access an array. And we don't need this branch to ever go here. So this branch never goes to that location. This could be completely different parts of the code. So this can come from one library, this can come from another, and it might be code that no one really uses. Oh, sorry, this code might be code that no one really uses. It's just there. Now, what do? We create a location that a program that takes this location here of this gadget and jumps to this location at the attacker code. And at the attacker code, we do a return or whatever we need to continue execution. And we do this branch once, and we do it twice, and we do it several times. And at some stage, our branch predictor will learn this branch. Once the branch predictor learns that, we call the victim, and we cause it to execute this branch. And again, the branch predictor will tell it where it thinks it goes, and this will go to the gadget, which will leak information from the victim. Now, these attacks are more insidious because we can attack kernel from user space or things like that. But in the other side, it's a bit more difficult to do that because we need to control much more data that comes into the victim. So, but still, it exists, and yes, there is we need to be aware of that. And probably when compilers introduce some countermeasures, but every countermeasure that we have is it causes a performance loss. So that's it basically on Spectre, Meltdown, and transient execution attacks. That's what I prepared. So I will be happy to take questions. That's an interesting question. So the question in the Zoom chat is whether Spectre works on architecture with delay slots such as MIPS. It's an interesting one. It works less, it's much harder to do a Spectre attack when the architecture is not out of order. So if it's in order, the attack is much reduced. I believe that it could work if you have enough delay slots or if you have enough prediction, but usually it more affects processors with deeper pipelines. So usually with out of order. I haven't seen an attack on a processor that is in order. Spectre attack working on a processor in order. And meltdown attacks affect mostly Intel. They do not affect, they almost do not affect AMD. They affect very few ARM processors. I think that they affect some others, but I don't remember the details. Elena questioned, how did you learn about the behavior of the CPU microarchitectural level, assuming that these details are not publicly available? So some details are available, or some information is available. The generic design of processors, out-of-order processors, is known. How to learn the details of things? We worked for Spectre. It was luck. We found out the right sequence. The same actually for Meltdown. And after that, we start trying to reverse engineer. So you come with an hypothesis, the usual scientific way, coming up with the hypothesis, come up with an experiment that either supports it or rejects it, and run the experiment. In a sense, once I started doing this type of work, I realized that computer science is a real science. And basically, we're like Luigi Galvani that took frog eggs and ran lightnings through them. And we're doing the same thing. We have a system that we don't really understand, and we try until we get some explanation. The explanation has improved over years. So what we thought was right in Meltdown is probably, when we published Meltdown, was probably not fully accurate. Today we know much better. AMD are vulnerable to Spectre. They are not vulnerable to the classical Meltdown. There is some leakage, if I remember correctly, there is some leakage from MSRs that is similar to Meltdown, but other than that, we haven't succeeded in getting any of the others attacks working on them.
Are you checking also questions on Discord, Yuval?
Yes.
Okay.
I hope I do it the right way, but I had one question there, and it seems that another is coming.
Okay, let's see. We have time.
Yeah. Okay. And the question is, Spectre, for those who don't have Discord, Spectre, Meltdown, and the like are CPU bugs, but for the attacks that are cache-based side channel, is it sufficient to use Cypher implementation that accesses memory in a pattern that is not dependent on the secrets, or are there subtle conditions where this is insufficient? So let's start. Spectre is probably not a bug. Spectre is a design feature, and it will be extremely hard to remove a Spectre from processors. We can probably defend partly, and we will have to learn to live with the consequences. Meltdowns are bugs, and most of the attacks published on the line of Meltdown are CPU bugs that will probably be fixed. So, for cached-based side channels, we believe that if the program meets 3 conditions, then it is not vulnerable to this type of attacks. And the conditions are that it does not use branches or control flow that depends on secret information. It does not use memory accesses that depend on secret information, and it does not use instructions whose timing depends on secret information. And the first 2 we can verify. The last one, we need the CPU vendors to tell us what is correct and what is not. There have been some attempts to reduce the requirements. So instead of saying that memory accesses do not depend on secret information, we say that cache line access do not depend on secret information. And we have seen that this doesn't work. There are attacks that can leak information in below cache line boundaries. Okay. Now, question from Zoom: is there a pattern of these design bug weaknesses? It seems that all of those somehow exploit measures introduced to improve performance. It's an interesting question. There are attacks that exploit contention on things that are not part of improving performance. So the fact that we have limited bandwidth to memory means that we can leak information just by having strange access patterns and find out what happens in other core, even if we don't have any performance improvement there. When we have performance improvement, the thing is that performance improvements what they tend to do is they tend to improve the general case. So they take the program and they say, we try to learn what the program does and behave according to that. So we have something in the processor that learns how the program worked and changes the processor behavior based on that. And if we have another process on the same processor whose performance is affected through that, then we have an information leakage. So this is performance improvements tend to introduce vulnerabilities. This is also true for software. The more complex the software is, the more vulnerability it is likely to have.
No more questions? Do you see
something coming? Seems that something is coming on Discord. Hopefully, possibly. While writing, we may have, if you are interested in things like that, we may have positions for PhD and for postdocs in Adelaide. So if you are interested, contact me.
Yuval, there is a question in Zoom now.
Yes. Okay, in Zoom, ARM processors most probably also use out of order and must be using branch prediction. So why are Intel processors more vulnerable to Spectre meltdown? So first, ARM processors are vulnerable to Spectre, just like Intel processors. I don't know about the most recent part, so I just got an M1 machine, so we could test that, but they might have defenses there. But before we had defenses, most processors have had the Spectre vulnerabilities, and the more complex the processor, the bigger the vulnerabilities. For meltdown, Intel is vulnerable because they made the design decision to allow execution with the unsanctioned data. They assume that it improves performance, it reduces the logic state, so it was more vulnerable. Other processors, some of them has done that. So ARM some ARM designs were vulnerable to meltdown. Other processors were not, and it's mainly luck. They just didn't go that path. No one really thought it was a problem. Are there any related attacks that could affect ARM-Ts similar to meltdown that would allow to disclose secrets? I don't know. I am not familiar enough with ARM-Ts. Most ARMs are not vulnerable to meltdown, and I don't know how ARM-Ts protect the memory. So it could be that they are not as vulnerable. I can't answer that. I haven't seen meltdown attack across ARM-Ts.